On binomial and geometric random variables. And kind of the weird thing is they're very similar, but there's a difference in between the two that makes it easy to distinguish. So for example, in a binomial distribution, there are usually two probabilities that you talk about, and one's considered a success and one's considered a failure. So for example, let's say I'm a basketball player and I have a free throw percentage of 75%. That would be considered your success. And your failure then would be 25%. And I shoot my baskets, and I say I shoot 10 free throws. And I want to know what's the likelihood that I, shooting 10 free throws, have whatever going on. So there's a determined amount of shots being made. In a geometric, it works kind of the same, except you say that I'm going to continue to shoot until I have a success. So everything is a failure up until that point in time that you have a success, and that's the difference. So in the binomial, you could say I make this many and I miss this many, whereas in the geometric, you keep missing until you make it. And that's the big difference. And you'll see that as we do our examples. So in binomial, we do several independent trials and record the number of times that this outcome occurs. And there are four conditions. Number one, binary, meaning that there are two possible outcomes. Number two, are they independent? Like, for example, whether or not I roll a sum of 5 on my dice the first time has no bearing on whether I do it the second time. How many trials I'm going to do? That's what they call the N in this situation, N number of trials. And then number 4, on each trial, the probability of the success has to be exactly the same. So that was referring to what I was talking about with the basketball shooting. So those are the 4 things going on in order to be binomial. When you're talking about the distribution of this binomial random variable, the x is the success, and the probability has parameters n and p, n being the trials, p being its probability. And then all the values are, for the x, are the whole numbers from 0 to n. So if I'm shooting 10 baskets, I could have 0 that I made, or I could have 10 that I made, and anything in between. That's what they're talking about. So example. In this example, we want to know when we roll a fair die 10 times, and x is the number of 6s, we want to know if we have a binomial distribution. So is it binary? That's the first question. You're rolling this fair die, and x is the number of 6. Is it binary? Can you get a 6 or not get a 6?
Yes.
Yes. Because the success is equal to the 6, and the failure is equal to not a 6. So that's okay. They're not talking about all the different possibilities on the dice when you roll those, but you can get a 6 or not a 6. Are they independent?
Sure.
Yeah. Getting a 6 does not preclude you from getting a 6 the next time, or guarantee that you'll get one. What about the number of trials? Do we have a certain number of trials? Yes, there were 10 of them. And then the last thing is, when you talk about your successes, back up above, in your successes, the probability is always going to be equal to 1 out of 6. So that doesn't change on each trial. So all 4 of those conditions have been met. Number 2. You shoot a basketball 20 times from various distances on the court, and y is the number of shots made. So when I look at that, what I see is, first of all, is it binary? Can you either make your shot or not? Yes. So you make the shot or you miss. That's what it means to be binary. Either you can do it or you can't do it. That's a binary situation. Independence. Does one shot determine whether or not you're going to make the next shot?
Mentally, maybe. Yeah, that's one.
Yeah, good question. Mentally, so there are some extraneous things, maybe what you would call a lurking variable about your mental state, but the actual shot or not shot,
No.
I don't know. I mean, a lot of us, because of the human factor, would say yes, but mathematically, I guess they would say no. So the answer is yes. It's independent. Just because I make one shot does not necessarily I make or miss. If I'm a coach, on the other hand, I'm a believer in the hot hand theory. So if somebody is really doing well in a game, whether it's basketball, hockey, or whatever, get the person the ball, get that person the puck, kind of thing. Number of trials. Is there a determined number of trials?
20.
Yes, they say there's 20. And then, so this part might be the part that you're talking about, the success part.
But then it's also various distances. So
That's right. So when they're talking about successes, if you were shooting a free throw every single time from the free throw line, your success would be the same each time because you're in the exact same position. So here, your success, when you're varying your distance, this might be the part where the success is not exactly the same. Because if you're shooting from 30 feet or wherever the free throw line is, that's exactly the same. But now if you shoot from the three-point line, your successes aren't exactly the same because a three-point shot and a free throw shot might have different success ratios or probabilities. So this is not the same because these trials are not always the same. So if you talked about your free throw percentage being 75%, but your three-point success being 50%, now your successes are different. These are not the same probability. And so here we can't necessarily talk about this in a binary situation. And then the last one, when they're talking about cars on the road and C is the color, binary means you see the color, C is the color. It doesn't say what the color is.
Yeah, but every car has a color, doesn't it?
That's right. So are there only two possibilities?
No.
No. There are more than two colors. So if you change the statement, like Madeline was saying, to say, do I see a red car? Then that could be a binary situation. Either it's red or it's not red. But if they only talk about it as the color and that's it, then that's not binary. A little bit about it, and I'll show you how to do it. The most important thing is that you're going to know how to do it on your calculator. So in this next one, they talk about the binomial distribution. And your possible values of your events are 0, 1, 2. How many events are you going to have? That's your n. And then k are part of those values. And here's how you find the probability. So let's say, for example, that you know the likelihood of having a girl is 50%, which means the boy is also, or 51%, excuse me, down here below. And then we're also going to talk about then, well, how do you know then if exactly two of them are girls? So you could have, like, out of having 5 children, you could have girl, girl, boy, boy, boy. You could have girl, boy, boy. There are a lot of different possibilities of how you would arrange that situation. So this first part right here, this NK thing, is talking about how you would arrange that. And then the second part is talking about the success and the failure. So the way that you would do the first one, if they're talking about exactly two of them being girls, I know that the probability of my event of having two girls, so X is how many girls you have, the equals 2 means I'm having exactly 2 girls. What I would think would happen is I'd take the probability of my girls, which are my successes, and that's 51%. And how many girls do I want? 2. And then if I fail, or I don't have a girl, which means I have a boy, that would be a 49% situation, and I know I would have to have 3 of those. And those 2 powers, or exponents, add up to 5, because I'm having 5 children. But the problem is that I could have many different arrangements of how I had those children. So the first part that we were talking about up here talks about how you would choose the ordering of those children. And that looks like this. 5, choose 2. It's not a fraction. It's the way you would arrange the order of how you would have those kids, or how you would choose those 2 girls, I guess would be another way to say it. And the way that you would type this in on your calculator, if you go into your calculator and you find this, binomial PDF, the way that you would type that in your calculator is you'd say that you're going to be having 5 children, and the probability of success, or having the girl is a 51% chance, or 0.51, and that you want 2 of those successes. So if you go into your calculator and you type that in, what you find out in either of these cases is you get a decimal, and I think, where do you find binomial PDF? Second vars. So try it, look for it. This is your probability.
So would we have to?
Okay, so in the second one, it says exactly 4 are girls, so we write down P of X equals 4. And that would be 5 choose 4. Again, it's not a fraction. I want the girls, which are 51%. There's going to be 4 of them, which means there's going to be 1 boy. And then I get 0.1657. And I'm not going to write down the calculator. You'd have 5, comma, 0.51, comma, comma 4. And the next one, for none of them girls, works the same. So the probability that X is equal to 0, and that would be 5 choose 0, 0.51 to the 0, and 0.49, and all of them would be boys. So to the 5th power, and I get 0.0282 as my answer. Now the last one out of all of these is the one that might be a little bit tricky. Gotta kind of think about what's going on. When you're talking about the probability of at least 3 of them being girls, that means X is greater than or equal to 3. This is talking about the probability of X being 3 plus the probability of X being 4 plus the probability of X being 5. So when you're demonstrating this, you can show each of these individual probabilities. Once you write this out, you could write down what the 3 probabilities are. So I have those already listed. I've got, and I'm going to show you one more thing after that, 0.3185 plus 0.1657, which I think we did already, and 0.0345 for a grand total of 0.5187. Okay, so that is the probability. But I want to show you something. Up here in our calculator language, we talked about when you have the probability of something being exactly 2, that your binomial PDF will tell you what it means to be exactly that number. You remember how in our tables and our staple packets, when we're looking at z-scores, that in that table it tells you the proportion that's less than or equal to that value in our distribution? There is a command in your calculator that